And so the second talk of the day is Frank Jiang, who's at KTH working with Carl-Henrik Johansson, I think.
Yes, that's right.
And also funded by WASP, Human-Centric Specification Framework for Connected Vehicles. Please go ahead, Frank.
Thank you. Thank you for the introduction. Yes, so like Peter said, I'm at KTH with the Division of Decision and Control Systems. So, uh, very control-oriented talk coming again. So, two control talks in a row. And so, oh, can I control? Okay, yes, I can. Good. So, if I start by talking about the motivation of the work, at the start of my PhD, so the beginning of 2020, we were seeing kind of a very rapid rise in the kind of excitement for autonomous vehicles. And I would say that, this has continued to kind of improve over time. But one of the things that we have seen over the last couple of years, especially, is that the complexity of deploying fully autonomous vehicles is it's becoming more and more clear that it's a lot more complicated than maybe a lot of
It's
folks
Lars.
and companies. Oh, okay. Uh, who knows? But yeah, it's a lot more complicated than people think, and then a lot of edge cases continue to kind of pop up as we deploy for longer and longer. And so, I think because of this struggle with getting to fully autonomous very soon, we have seen also that there has been an increase of acceptance for remote human support. And so here I have a picture of a fairly famous Swedish startup, Enride, and the remote operation station that they have set up for their pods. And it's not just Enride doing this. Actually, many autonomous vehicles have had a control center connected in the background somewhere throughout basically all of their operation. It's just starting to become also more and more public, and there's more and more awareness around this kind of need for remote human support for these road vehicles. And for us, it was not so surprising that this is a phenomenon that has kind of stuck and is starting to grow more and more. Because if we look at the aerospace industry, the need for human operators is it's not very new and not very surprising, right? So uh, one could argue that airplanes are one of the most well automated systems that we have deployed in the world today. And yet, even though they are very highly automated, we still have a human pilot on board the vehicle, and we have humans sitting in the control tower. And so the reason for this isn't really because the airplanes are cannot take off and land by themselves, but it really is because when exceptions happen and when system failure happens, we really kind of it is integral for the safety case that we have human response built into the system. And although we can learn from the aerospace industry about kind of the need for humans, it turns out when we really started to dig into uh, the, how to add human support for road vehicles, we realize that there is a fundamental difference between uh, how airplanes are deployed versus how road vehicles are deployed. And the main big difference is the fact that a requirement for autonomous vehicles and for the business cases that autonomous vehicle companies have is that there should be no human driver sitting in the car. And this is super different than in aerospace, because in aerospace we rely on the pilot, and not even just one pilot, but oftentimes two pilots to be there to be actual system failure fallbacks for the airplane when something happens. Uh, and we have a road vehicle that we're deploying, and we're saying that we cannot have any humans on in the front at all. And we only have this human who is connected remotely. And so this means that the role that the human also has is also fundamentally different because they are expected to both handle quite low level tasks while still handling higher level tasks. For example, in air traffic control, the role of handling routing failure. And I think when we saw this kind of key difference, it was very motivating for us, and we became very interested in thinking about from a control perspective how we should actually rethink how we are automating these vehicles and rethink the relationship that the human should have with the automated system. And kind of one of the core principles that we leaned into a lot was the idea of human-centric design. And when we apply this human-centric design thinking to the control framework, what we realized was is that kind of we need to actually think about how to do the control design by first looking at what the role of the human actually will be throughout the operation of the vehicle, and not do maybe what we classically have done in the control community, whereas we build a control system and then we add kind of some kind of exogenous or external support for humans to interact with the system, right? So we want to actually think about the control design from a human-centric perspective in the beginning. And kind of some of the examples that we kind of looked into in this direction is first that these human operators, they will oftentimes need to intervene and try to understand what the vehicles are doing. And for this, we want it to be possible that the kind of human operators who maybe don't know anything about control can actually specify and even update tasks that the automated vehicle is doing and not make mistakes. Okay, and then for not only that, but like I mentioned before, we also want to kind of in this environment and context, we want to be able to support both low and high level tasks and interactions because the human might need to do both for supporting these automated vehicles. And when we support this, one thing that was very important for us to kind of keep in mind was that when the human is actually interacting or maybe even taking over the vehicle's control, we actually want to also maximize the human operating freedom, because one thing that maybe isn't always so clear is that kind of the role, since the human is actually connecting to the vehicle to take over and handle system failure, in these cases, it's oftentimes the case that we cannot over rely on the automated system to actually make decisions on its own. And then this means that we actually need to kind of give as much capacity as we can to the human and maybe just prevent them from hitting the wall by accident. And then I think the final thing that we thought about was kind of how we could manage to minimize the human error that we're actually injecting back into the system, because the whole idea with taking humans out of the loop, or one of the ideas for safety, is that humans make a lot of errors and autonomous systems are kind of very precise and very smart. And here we're arguing for making sure that we can always put a human back in. But when we do that, we need to also make sure that we're not introducing the human error back into the system. Okay, so when we were thinking about doing this, we kind of we kind of looked into a lot of the safety methodology for how to do this, because we believe that when we're adding these humans in, it's fundamentally a safety problem. And in the control community, I would say kind of there are two toolboxes that we often reach for doing safety work. The first one is a theory called formal methods. And for those who aren't familiar with formal methods, it's basically a theory that kind of allows you to give requirements to a system and actually verify that those requirements can be fulfilled and will be fulfilled by the system. And traditional formal methods theory is very powerful, and you're able to actually describe very, very complex tasks. Uh, but one of the drawbacks with classical formal methods is that it's oftentimes hard to actually embed very rich dynamics into the formal methods analysis. So if you have a system that, for example, like a car or an airplane, that kind of has very interesting dynamics that you want to keep track of and incorporate in the tasks, this is kind of difficult to do in the classical formal methods approach. Whereas in a more control theoretic side, there is a theory called reachability analysis, where uh, where this kind of discipline has been geared around taking dynamics and very low level phenomenon, for example, like wind, which was brought up in the previous talk, and actually kind of building a safety case and making sure that the system is actually able to react to uncertainties and always maintain the requirements that we have given to the system. But then the issue with reachability analysis is that it oftentimes becomes very, very complex and unwieldy when we need to build very complex tasks. And so kind of our perspective on this problem then became that kind of if we want to build out a human-centric framework, we were interested in combining both the benefits of formal methods and reachability analysis so that we can create a framework that can handle rich dynamics that often pop up in cyber-physical systems. And then we can also specify very kind of intuitive, complex tasks for the system to complete. So what we developed, and I won't go into the details of this too much, but I'm happy to send any papers that for people who are interested. But essentially what we developed is we created a end-to-end pipeline based on a tool we introduced called temporal logic trees, where essentially we can take in at the very beginning a high level requirement specified in the temporal logic formula. And then we can convert this into a temporal logic tree, which is built then using reachability analysis. And then in the end, we actually can compute and synthesize a feedback control set. And this feedback control set can then in downstream be used for either for just doing safety or liveness filtering. It can be given directly to MPC as an input constraint, or what the example I'll give more insight into later in this talk. We can also pass it on to shared autonomy systems, and we can use it to facilitate the interaction between the human and the autonomous system. And before I jump into the overviewing the methodology, one point I just want to make here is that I was very careful to call it a control set that we compute at the very end, because one thing that has been very important with this methodology is that we want to have, after we give a requirement to a system, and it checks that the requirements are correct, and then finally tells what the system to actually do. We wanted the output of this to actually be a control set. So for example, if we talk about accelerations for a vehicle, as opposed to on the left where we have like traditionally what we would call a control policy, so a single acceleration value at each point of time. On the right, at each point of time, what we want to output is actually a set of accelerations that describe kind of the full range of accelerations that are acceptable for the vehicle to fulfill. And I'll explain more why that's very important in terms of the human-centric perspective. So without getting too much into the details, this temporal logic task, for example, using this type of formulas that I show on the left, you can actually kind of describe the requirement that we have on the right. So you can ask the system that say that it needs to park into one of these parking spots. If your charge is too low, you need to, or if you're low on fuel, you need to go and refuel. You should always avoid these things and those things. And so you kind of you can describe tasks that are very intuitive from a human perspective, and the way we usually talk about kind of instructions for a system when we're trying to get them to do what we want to do. And then I brought up reachability analyses, but essentially, what we have specified is the definitions on the left. And with these temporal logic tree frameworks, what we have done is that we have actually specified the reachability analysis, the assumptions and the conditions we have around the reachability analysis, and don't actually prescribe a particular type of reachability analysis, so people can come in with any kind of tool that they prefer. Here I give an example of using a particular formulation called Hamilton-Jacobi reachability analysis, where essentially we specify that kind of once you're given a goal or a particular task, what does the reachability analysis actually need to compute for you to construct a temporal logic tree? And then using these definitions, what we can then start doing is actually build the temporal logic tree from the bottom up. So here I have a couple of examples. On the left, for example, we have T on the bottom of one of these fragments, and T is some kind of target that our system needs to fulfill. And then using the formulas that I described in the previous slide, essentially you can provide a constraint for the system to that it needs to respect when trying to reach this target. And then this will form kind of one fragment in the tree. And then what you can do then is like you describe this whole task, and then this tree gets formed. So from the bottom up. So if we take this parking example, so in the parking lot that I show in the small picture, we have two parking spots that are colored in green, parking spot 1 and 2. And then in the tree on the left of the parking lot, you can see at the very bottom of the temporal logic tree, we have parking spot 1 and 2. And then there are a couple of set operations that are applied to these parking spots going bottom up. And then the operations that are used throughout the tree are actually based off of this kind of high level requirement that the human actually gave to the system. And then the kind of really neat and clean result that we ended up with is that once you actually build up this tree, the node at the top of the tree actually contains all of the states that the system, like the vehicle, needs to start in to be able to fulfill what the human originally asked the system to do. So essentially, in this blue region that I've colored here, you just need the car to start in one of these states, and then based on the analysis, the car will be able to park in one of those spots with guarantees. So this is kind of a different way of doing model checking, and the result is kind of I think fairly simple and nice. And then once you have kind of found that it's actually possible for your car to do it, what we then do is that based on the location of your car, so if you ignore kind of the equations on the left, unless you're interested, and you focus on the picture on the right, what we can do is based on this tree is that actually in real time, we can actually take a look at where your car is and tell the car exactly what the max acceleration it's allowed to have, the min acceleration it's allowed to have, the max steering and min steering it's allowed to have. And as long as it picks a acceleration and steering within these limits, then the requirement that the human originally asked for is guaranteed to be fulfilled. So in fact, you can just randomly choose accelerations and steerings. You'll get a really weird behavior out of the car, but you can just randomly choose accelerations and steerings out of these sets, and then the final parking task will be fulfilled. And when we evaluated this technique in real time, we found that we were actually able to synthesize these sets at 50 hertz. So this is definitely something that can be used in real time. And so this example here, where we bring back the same parking lot that I showed earlier, where we can actually show that we have this parking task that I talked about before, but then partway through the parking task, so you can see kind of the car's position updating over time. Partway through the parking task in the picture on the right, part of the parking lot actually gets blocked off. And you can see actually that our synthesis approach is actually able to react in real time quite easily to this type of change. And for each position that the car is in, we have this small green square, which describes the kind of control capacity, the steering and acceleration that it's allowed to implement. And so on the pictures on the left, you can see that it has full steering and acceleration capacities. And then on the right, you can see as it approaches certain constraints, it's being forced to turn right at different accelerations. And right before it parks, it also is forced to turn right. Right. And so what we did is actually we took this pipeline and we applied it to a safe teleoperation task. So the task that we gave the human to do is to park the car at a 90 degree in one of the empty spots while avoiding full parking spots and the parking lot walls. And then we also ask them to maintain a kind of a maximum velocity throughout the parking maneuver. And so here is an example that we implemented in the lab using a scaled down vehicle. So this experimental platform is also connected to the 5G network that was deployed at KTH some years ago. And so then you can see here that he has been instructed about what the task that he should complete is. And then here, the system is actually kind of allowing him to implement whatever controls he wants until he hits a boundary of the control sets. And so just now it actually he was oversteering or understeering. And then here it happened again. And then it actually adjusted and forced him to kind of back up and readjust his angle. And then for the final maneuver, he then kind of let the system complete the task in a way that's precise because he leveraged and triggered the automated vehicle's control input. So here's just a kind of a simple example of a deployment of this pipeline where kind of we're able to actually you know move between the human's input and the safety input in a way that's very fluid and kind of leaves a lot of the control and decision making actually in the human's hands. Okay, so that was kind of a quick overview of how we've deployed this system for teleoperation systems. There's a couple of important extensions that we have added on top of this framework. So the first one is that when talking to our collaborators and in industry, we realized that kind of it's not just specifying tasks for a particular vehicle that is important, but there's many, especially kind of, for example, cities or traffic management agencies, where they would actually like to specify specifications or tasks for regions. So an intersection should have a particular behavior. And it's not that every vehicle should be specified on its own, but the intersection itself should have some properties that are specified and respected. The other aspect is that oftentimes in these environments, there are pedestrians and human-driven vehicles. And as obstacles, when you apply reachability analysis, they can be quite difficult to handle because it's hard to kind of handle the uncertainty about the decisions that they'll make. And then finally, we've been working on better tooling. So we use a lot of Hamilton-Jacobi reachability analysis, but we're kind of looking at a lot of different other reachability analysis forms to do the same temporal logic tree constructions. And then we also are working on kind of new intuitive representations of the tasks because temporal logic formulas are not exactly very accessible for human operators. And I can just give some quick pictures of the kind of these directions. So here is some intersection specification that we have shown. So here we show that we can do actually multi-agent temporal logic trees. So specify, like I said, the behavior for the intersection, and then you can see kind of all of the reachable sets and all the kind of flows of the vehicles through the intersection are being analyzed, and then each vehicle is actually being told the steering and acceleration limits they're allowed to implement in order to pass through this intersection safely and efficiently. And then we've also done this work, followed up on some of this work on how to handle the pedestrian safely. So on the picture on the left, I show an example of kind of the problems that pedestrians often cause. So in the red set, you can see that if we try to predict where the pedestrian will go, they can go a lot of different directions, backwards, forwards, and different speeds. But we know that it should actually intuitively, when we're trying to coordinate these vehicles, we should actually be planning on them following the green set that I've drawn here. And so one of the things that we leverage is actually we developed a framework based on data-driven reachability analysis and transformer encoders to actually reduce the red set on the right down to the blue set that I show. So in the black dot, we have the pedestrian's position, and the white line is the kind of true future trajectory the pedestrian followed. And so we can show that we can actually predict quite precisely where the pedestrian is going to go using these data-driven techniques. And the last thing is that we have also open source. So if anyone's interested in trying out these techniques, we have open sourced the temporal logic tree construction tools in Python. And there we also abstract away the reachability analysis so that kind of we can do comparisons between, for example, Hamilton-Jacobi reachability analysis and hybrid zonal tools. Okay, so if we finish up with conclusions. So I think kind of throughout my PhD, I think what we really came to understand is that when doing control design or kind of with focus around the role of the human operators, we find that kind of there's a stronger need for intuitive specifications and automated verification to kind of handle the error that humans might introduce into the system. We have a motivation for these kind of control sets that I talked a lot about throughout the talk. And then for next steps, we are kind of interested in pushing more on different case studies now that we have these new approaches for handling regions and pedestrians. And then we also are working on better tooling. So we are soon, hopefully in the spring, we'll be releasing an integration with behavior trees with the full pipeline. And I wanted to quickly thank my collaborators throughout the PhD. And that wraps up my talk. Thank you.
Thank you. Virtual applaud again. That was very interesting, Frank. Questions? Okay, so I have a question to begin with. So in the example, when this guy was driving the little the mini car there, so I guess he was trying to turn left, right? But he was turning a bit late, and then the car automatically backed up. Was that correct?
Yes. So, can I not control it? So yes, so that was correct. So apparently I cannot control the scrolling of the video right now on my screen. But yeah, so you can see basically in this beginning part, he is fully in control. And then it's when he first starts turning after the trailer here.
Kind of soon. He's late in the left turn, right?
Yeah, so here it understood that he wasn't going to make it. And so now it adjusted him. And then now again, it saw that he was not steering enough to reach the empty parking spot. And then it kind of got him back to a state where he actually can make it into the parking spot correctly.
Cool.
Yeah.
But I guess, I mean, okay, so I mean, this is very cool theoretical work, but as it works now, I guess he would be a bit annoyed if he was driving a real car that did this, right?
Yes, I think so. I think in this case, we kind of let him like learn how to use the system, and then I think he kind of started to play around. So we gave him the option to turn off the system correction system completely. And so what he actually did is he actually ended up changing the ratio, the blending ratio between him and the system, uh, that I guess that he felt comfortable with. But I agree with you that I think he could get upset, and so that is something that I think would be interesting to dig more into in terms of both improving the system at understanding his preferences, but then also improving the system in terms of uh, kind of or studying better kind of how his emotions are throughout using the process of using the system. Yeah.
It's very cool. Is there any questions from the audience? Okay, so well, at the end there you said there's a parameter of blending his input and the system input.
Yes.
So
Yeah.
I guess
So I
the systems gives kind of an allowed set, right? The control set, not the control action. Okay, yeah, go on.
Yeah. So the essentially what we did here is that there's still a control limitation in the end. But then what we did in this particular experiment is that we did actually try to infer a bit. I mean, we had a very simple inference setup, but we try to infer a bit what he would want to do. Uh, and the system then proposed him doing this. So basically what it was doing, it was seeing that he had this task of parking, and it proposed the optimal control, time optimal control to do that parking for that parking spot that he was closest in the time optimal sense. Uh, and it proposed this to him, and then the blending, so this alpha term here that he was in control of is he could basically control the how much he was in control versus this proposed control input was used. But both all of them are within this control set.
So some kind of average between his control and the time optimal, as long as it's in the allowed set. Is that
Yeah. It's a convex combination between his input and inferred input.
so? Could you? So this has a flavor of kind of being a more advanced version of Lyapunov stability to me, because since it kind of gives you a set, and while you're in the set, you're guaranteed to converge. Is that a good mental model, or
Yeah, that's a really good mental model. The thing that I think is interesting is that so the technique, the reachability analysis itself, I think the cool thing about it is that it's very constructive. So, as opposed to the Lyapunov techniques, where you maybe often are stating a particular, Lyapunov function to be used, here it is iteratively kind of found and generated and synthesized. But then I think the properties of the Lyapunov function itself and the theory that kind of extends from there, I think is somewhat related to what's happening here, but this actually could be improved a lot by actually adopting kind of the Lyapunov theory.
Hmm. Thank you. So I guess it's time to end this session. So thanks again. Great talk, Frank. Very interesting.